In this practice problem, I'm asking you to synthesize this alcohol right here, the tertiary alcohol, and you are permitted to start with aldehydes or ketones of 4 carbons or less. What that means is any carbons in this final product must have come from an aldehyde or a ketone that had 4 carbons or less. All right, so the first thing we want to do is recognize that this molecule here has a lot more than 4 carbons in it, and specifically a lot more carbon-carbon bonds than we're permitted to start with, which means we're probably going to use organometallics to form carbon-carbon bonds at some point in this reaction, maybe even multiple times. So what we want to do is we want to work backwards, trying to continually get back to alcohols, because every time we get back to an alcohol, that's a moment where we can split the molecule apart to figure out what the starting materials were, right? So here we have a tertiary alcohol. Now we have to keep in mind, anytime you use an organometallic like a Grignard or an organolithium, if you use that with a ketone, it's going to make a tertiary alcohol. So what we're going to look to do here is split this in half into some sort of ketone and some sort of Grignard reagent or organolithium reagent. So what we need to think about is, where's that new carbon-carbon bond that formed? Well, anytime you're doing these, remember, this carbon oxygen bond at one time was the carbon oxygen double bond of the ketone that we're using, which means that either this bond here, or this bond here, or this bond here is the new carbon carbon bond, right? So we need to think about where we're going to split this thing apart. And there is no one way to do this. Okay, but we're going to pick one direction and we're going to go with it. Now, let's talk about this carbon-carbon bond first. Can this be the new one? It could be, but that'll give us an entity here on the left side of this bond with 3 carbons. Which we're permitted to start with, but that would leave the entity on the right side with possibly too many carbons. So what I'm going to do here is I'm going to kind of notice that this has a 4 carbon portion right here. So I'm thinking maybe this was a 4 carbon portion. This right here, 1, 2, 3, 4. Maybe this was a 4 carbon portion. This one here, 1, 2, 3, 4. This was a 4 carbon portion. So I'm probably just going to start with things that have 4 carbon portions. All right, so what I'm going to do is I'm going to go ahead and just pick one of these bonds. I'm going to pick this one right here, and I'm going to say that's our new bond, okay? Everything on the left side of this bond must have been the ketone. So that includes all of this must have been the ketone. Everything on the right side right here must have come from the Grignard reagent. So what I'm going to do is I'm going to split that bond in half, and I'm going to keep everything sort of drawn the same so we can kind of just keep track of where everything is. Everything on the left side must have been that ketone right there. Everything on the right side must have come from something like this. So there's the magnesium metal, and I'm going to go ahead and say chlorine there. Doesn't have to be chlorine. You could have chose bromine or iodine. Um, right? Now, every time we do these, when that ketone and that Grignard react with each other, we're going to do a second step where we throw in the acidic workup. And what that does is that puts the proton on the oxygen here, right? So we split those two things apart. Now we're going to have to work these things back to aldehydes or ketones of 4 carbons or less. Let's focus on this Grignard first. So we're going to work this thing backwards. So the question is, how do we make a Grignard? Well, anytime you make a Grignard, you make it from the corresponding halo alkane. So I'm going to go ahead and draw that 4 carbon chain, and I'm going to put that chlorine back on that carbon right there. And the way we make that transformation is by using magnesium metal in some sort of ether solvent. Usually I just pick diethyl ether. Doesn't have to be diethyl ether though. Then we're going to focus on this halo alkane. I'm going to ask myself, how can I make this? Keeping in mind that I'm eventually going to try to work this thing back to an aldehyde or a ketone, an aldehyde in this case, since that is on a terminal carbon. All right, so I'm kind of thinking, all right, well, how can I sort of put an oxygen on this carbon right here? How could I had an oxygen there and converted it to a chlorine instead? Well, what if we had the corresponding alcohol, this structure right here? How can we make that transformation? We can use HCl We can use SOCl2. We can use PCl3. I'm just randomly going to choose one here, and I'm going to use SOCl2. It's a good SN2 mechanism. It'll work on a primary substrate like this. Now I'm going to focus on this alcohol, keeping in mind that I got to work this thing back to an aldehyde or a ketone, an aldehyde in this case. And I'm just going to ask myself, how can I make an alcohol directly from an aldehyde? Is it possible? Yeah, I could have had this aldehyde right here. And the way I can do that is I can reduce that aldehyde using something like lithium aluminum hydride, a hydride transfer reagent, followed by an acidic workup, which puts that proton on the oxygen. So that worked us back to this 4-carbon aldehyde, which is one of our permitted starting materials. All right, but we're going to come back to this ketone now because this still has way too many carbons in it, and we got to get back to aldehydes or ketones of 4 carbons or less. All right, so keeping in mind that we have to split this thing apart at some point, and every time we do that, we're going to have a Grignard in some sort of electrophile, like an aldehyde or a ketone. Every time those two things react with each other, they form an alcohol. So I'm kind of looking at this ketone and thinking, can I work this back to an alcohol? So I'm saying, how can I make a ketone? Can I make it directly from an alcohol? Yes, of course I can. I can take the corresponding alcohol, which would be this structure right here, the secondary alcohol, and I can turn that secondary alcohol into this ketone by doing an oxidation with something like PCC, or you can use the Jones method. And now I'm going to focus on this alcohol. And remember, every time I get back to these alcohols, this is a good time for me to split this thing apart. I'm kind of looking at this carbon-oxygen bond. Let me zoom in here. I'm looking at this carbon-oxygen bond, and I'm saying to myself, that must have been my carbon-oxygen double bond at some point. Okay? Until either this bond came in and reduced it or this bond came in and reduced it, right? So I'm going to split this thing at one of those bonds, either this one on the left or the one on the right. Either one's fine, but I'm going to make this less steps by choosing this bond here. Why am I doing that? Kind of have to think ahead a little bit here. If I split it here, then I have to do more reactions because this is a 3-carbon entity, which I'm allowed to start with. The problem is everything on the right side of this bond is now a 5-carbon entity, which I'm not allowed to start with in the rules of this question. So I'm going to split it here because that makes a 4-carbon portion and a 4-carbon portion, right? So this is the bond I'm going to split right there. All right, well, that is a secondary alcohol, and I know I can make those by using some sort of aldehyde with a Grignard reagent. So everything on the left side of this bond must have been the aldehyde. And how do I know that? Because that's where the oxygen is. So this must have been the carbon-oxygen double bond. So I'm going to go ahead and draw that aldehyde right there. All right. That is what's going to react with everything on the right side at this carbon specifically at this 4-carbon chain. So that must have been a Grignard like this. And I'm just randomly picking bromine here. And again, every time we do these, there's an acidic workup step to put that proton on the oxygen. All right, well, we're allowed to start with this thing here, this 4-carbon aldehyde, so we don't need to take that back anymore. So let's focus on this Grignard reagent. And again, I'm just asking myself, how can I make a Grignard reagent? You can always make these from the corresponding haloalkane. So I'm just putting that bromine specifically back on that secondary carbon. And I can do that transformation by using magnesium metal. And again, some sort of ether. I just like choosing diethyl ether. And now I'm going to focus on this haloalkane. Remembering that I have to make this thing from an aldehyde or a ketone. In this case, it's going to be a ketone. But but before I get there, I'm going to try to figure out how can I have had an oxygen on that carbon there. Well, it could have been an alcohol, this alcohol right there. How can I make that transformation? A lot of ways. I could use HBr. I can use SOBr2 or PBr3. I'm just choosing HBr here. And then the next question is, how can I get this alcohol directly from a ketone? Well, it's a secondary alcohol. We know that we can take ketones and we can reduce them to secondary alcohol. So I can reduce them with something like lithium aluminum hydride, followed by an acidic workup. Again, that's to put that proton on oxygen. And that leaves me at this starting material here. So I'm back to 4 carbon aldehydes or ketones, which I'm permitted to start with. So this would be a proper synthesis for this molecule here. And again, it's not the only way to make it. It's just one possible way.